Okay, so with this problem, you can see that this sort of mathematically tells a story that you kind of know intuitively. Um, if you started with a cantilevered beam like this, and uh, it was, being slowly pulled off the wall by its weight, where would you expect this thing to be in the most risk of breaking, or deformation? Uh, I suppose from experience that the problems are going to be over here where it connects to the wall. And that's exactly what we see here. There's not any contribution for tension, but the shear force and the bending moment both say that that material is having to do the most to stay in equilibrium right near the wall. Okay, so that's sort of what this is for. So let's do one now with let's do another example. But this time, let's say that it's not the weight we're dealing with, it's a triangular distributed load. So let's say well, actually, let's say that there is a pin joint over here and a roller at the midpoint. And a triangular distributed load where at its highest point you have a distributed load of 10,000 newtons per meter. And let's say this is 1 meter and this is 1 meter. So I mentioned last time that when we do our cuts, we're never going to get to this pin joint here, right? So we don't have to know what that is. But unfortunately, we are going to get to this roller. That is going to appear in it. And there's no way to figure that out without figuring this out with the tools we have right now. So the first step in this is we're going to have to calculate the external loads. Okay? So to calculate the external loads, we'll isolate the whole beam. And now that we've chosen what to isolate, we can treat that distributed load as a point force. Where is that point force going to act? Yeah, 2/3 of the way from here, 1/3 of the way from here. So it's going to be like this. Yeah, 2/3 of a meter from the pin joint. And what's the magnitude of that force? 10,000. 10,000 times 2 divided by 2. So 10,000 newtons. And then here we have force vector. Call that RP for pin. And then here we have a force in a known direction. I'll call that R for roller. And we're ignoring the weight on this one. I didn't give any mass. So Newton's second law says 0 RR plus 0 negative 10,000 plus RPX RPY is equal to zeros. And then the rotational equation. Let's take our moments about P, about the pin. So let's see. We have a moment with a moment arm of 2/3, 0.67 meters, times 10,000 newtons, and would that cause a clockwise or counterclockwise rotation? Counterclockwise, because this is the about point. And so that is positive 6,667 Newton meters. Then what's the moment produced by RR? 1 meter times RR, that's a clockwise moment, so minus RR is equal to 0. So RR is equal to 6,667. And RP is equal to 0x, and then positive 3,333y. So we have an upward force in the middle of 6,667, an upward force at the end of 3,333, and a triangular distributed load with a height of 10,000 newtons per meter. And now we're ready to do the cuts. How many important points are there? There's always the 2 endpoints. Are there any other ones? Yeah, where the roller is. So we're going to have 2 cuts. The first one is going to be for x values between 0 and 1, and the second one is going to be 1 and 2. So cut 1 for x values between 0 and 1. So we won't have gotten to the roller yet. So what loads are there? There's T, V, M. Those are always there in these internal loads calculations. And then now let's think for a second about, so picture what isn't included. Okay, so there's that. And all of that has this distributed load on it, like this, right? The piece that we're isolating doesn't have all of this distributed load on it. It just has the piece that's acting on our isolated part. So we're only concerned, it's still a triangular distributed load, but we're only concerned with the part over here. The thing that's sort of tricky about this is now we don't know what the height of this is, right? We know what the height is over here, but that's not acting on this piece. So we're going to have to use the equation for this line to figure out what the height is, at x meters out from the left end. Okay, so what's the line that represents? Yeah, so the slope of that line, you can think of this line as represented by y equals, now rise over run, it's rising 10,000 over a distance of 2. No y-intercept if this is your origin. And so that says that at this point, we have 5,000 x newtons per meter. Okay. I mean, we came up with a function of the height in terms of x, and then x is what we're dealing with here. You know, like the question is, if you go out x from the left end, how high do you go? And the answer is 5,000 x because of this function we found. Any questions about that? All right, well, now that we've chosen what to isolate and we know a height of our triangular distributed load, now we can represent this distributed load as a point force. Where is that point force going to act? 2/3 x. So here somewhere. And what's the magnitude of it? 5,000. So 5,000 x times x divided by 2. You're just calculating the area of that triangle still. You just have a bunch of x's in there. So the magnitude is 2,500 x squared. And then you have your internal loads. So Newton's second law says we have, if this is our about point, would the 25,000 x squared cause a clockwise or counterclockwise moment? Clockwise, so we have negative 2x over 3 times 2,500 x squared plus m minus vx is equal to 0. Yep.
One more time, how did you get that 2,500 x squared?
We just have a triangle.
I mean, like, what would you multiply?
Yeah. So we have a triangle whose height is 5,000 x and width is x. So it's 5,000 x times x divided by 2 to get the area. So 5,000, question? Oh, yes, I got just so excited about doing that one because it's so complicated. Okay, so we have 0, negative 2,500 x squared plus t negative v is equal to zeros. So t is still equal to 0. And v is equal to negative 2,500 x squared. And then rotational, we have negative 2x over 3 times 2,500 x squared plus m minus vx is equal to 0. And so m is equal to, this all comes out to be positive 1,667x cubed plus vx, and we know v is this, so that gives us positive 1,667 x cubed minus 2500 x cubed and so you get a final value of negative 833 x cubed. Okay, so that's the first cut. One thing you can check after each cut is you can make sure that derivative condition holds. So does dm dx equal v? Yeah, so that's good. So now we can go on to cut 2. So cut 2 is valid on the interval 1 to 2. We still have a piece of the triangular distributed load. This distance is x. So if this length is x, what's the height of this triangular distributed load? Still the same, that's right. So this is still 5,000 x. We have the internal loads. Anything else? Yep, now we have the roller. So somewhere in here, we have an upward force of 6,667. And this, we know, is at a distance of 1 meter from the left end. So now that we've chosen what to isolate, we can represent that distributed load as a point force. And all the math works out the same on this as it did for cut 1. So we have a downward force of 2,500 x squared acting with a moment arm of 2/3 x. And then we have T, V, and M. Okay, so Newton's second law says 0, negative 2,500 plus 0. Question? Yes. Thanks. Okay, plus 0, positive 6,667 plus T negative V is equal to zeros. So T is equal to 0, V is equal to negative 2,500 x squared plus 6,667. And the rotational equation. So we have a clockwise moment of 2x over 3 times 2,500 x squared. So that's same thing it was last time, minus 1,667 x to the third. Then we have a counterclockwise moment produced by the 6,667. It has a moment arm of 1 meter, so that's plus 0.6667. Then we have the bending moment, and then minus Vx is all equal to 0. So m is equal to positive 1667 x cubed plus Vx, so minus 2500 x cubed plus 6667x. And so you get a value for m of minus 833 x cubed plus 6667x. Yes. Yes. Okay, so that should be added on there too. Yep. Yeah. Plus 6667. Is that right? Yes. Excuse me. Okay. Now, right? Okay. So now we have these piecewise functions. T is equal to 0 for everything. V for the first half is equal to this. And for the second half is equal to this. And m for the first half is equal to this. For the second half is equal to this. So what do these functions look like? I don't know. Let's not plot these. But we can do those 4 checks to make sure that it works. So what we already checked was that dm dx is equal to v for the first half. So let's check that it holds for the second half. So derivative of this is equal to this. Derivative of this is equal to this. Derivative of this is 0. So that all works. So the first one, dm dx is equal to 0. Check. Yeah. Sorry. Is equal to v. You know, the problem is I start like thinking about, like I'm trying to do this while I think about like what comes next, you know? That doesn't work. I need to be in the moment. And then the second one is, are there any horizontal point forces at either of the ends? No, so tension should be 0 at both ends. And we got tension equals 0 everywhere, so that one checks out. Now vertical point forces. Are there any vertical point forces at either end? I can't remember. No. Yeah, there is one over at the right end, but not at the left end. So V should be equal to 0 at the left end. And if you plug, oh yeah, so this is not valid on the first, on that first interval, right? This function is valid only on the second half of that beam. So in order to figure out what's happening when x is equal to 0, we have to go back to that first function. Yeah.
So if those two functions don't match up, you just draw a vertical.
Yeah, that's right. Just connect them. That's just because that's what people do. You know, it's not, there's not really any justification for that. Yeah, that's what the cool kids do. Um, so if we're looking for what v does when x is equal to 0, we go to that first cut, plug 0 in for x, and we get that v is equal to 0. So this one checks out. And then the last one, are there point couples at either end? No. So m has to be 0 at both ends. At the left end, plug in x equals 0, and you get m is equal to 0. So that's good. And then for the second one, can someone plug in 2 for x for this function? No? Oh, you got something besides 0? What? How big is it? Okay, yeah. So if it's under about 50 or something, you know, like with the magnitudes that we're dealing with, that's just round off error. So it was something like that. Okay, yeah. So that checks out. You know, I rounded off I didn't keep any decimal places or anything. So, okay, so that's how those go. Any questions about that one? Okay, now you can imagine doing those with any shape of distributed load, right? Like you could do it with parabolic distributed loads and stuff. But sometimes, you know, these things get more complicated when you make the cuts, just like we saw with that triangle. We had to figure out a new way to represent, in terms of x, what the highest point was. And so so I want to show you one more of these. I don't know if we'll quite get through this, but let's do one now where the triangular distributed load. So let's say it's a cantilever beam. Okay, so far so good. This is what you like to see for internal loads problems, because all of the loads are at the right endpoint, so you don't have to calculate any external loads. So that part's good. And now let's say that there's no loads except this triangular distributed load. Like this. And let's say that this is 1 meter long. And let's say that the triangular distributed load has a maximum of 5,000 newtons per meter. So that looks just like a simpler version of the last one we did, right? But notice that the triangle is oriented the opposite way that it was last time. In rigid body problems, that's no big deal. But since we're doing all our cuts from the left, this is sort of a nuisance. So, because watch what happens when you make a cut here. So, so we don't have to calculate this external load because it's never going to come into problems. So we have some force here we don't care about, some couple here we don't care about. We have this distributed load, so let's figure out how many cuts we have to make first. We have to make cuts at the two endpoints. And then the distributed load is the same function the whole way, so all we have is 2 important points, 1 cut. So it's all good news so far. But look what happens when we make this arbitrary cut. So say our cut is this. Okay. Well, so yeah, let me just go through this and then we'll think through it. There are a few ways to think through it. So now we're only concerned with the part of the distributed load that's acting on this red piece, and that means this. And that means that our distributed load isn't triangular anymore. The good news is we get to use this 5,000, but the bad news is it's a trapezoid now, and we have to deal with this, kind of messiness. So the way I do this is I come up with, okay, so now this is a trapezoid distributed load. And that's a nuisance. One thing you could do is you could work from the right side. But I want you to be able to do this because like on the practice problems, you'll see there's one problem on there where whichever side you go from, you have to deal with one region that's where you get this trapezoid, So the way I do it is I break it up into a triangle and a rectangle. The height of this is 5,000. The height of this, since the width is x, if you figure out the function for this line, that gives you the height of the rectangle. And so that is y is equal to yeah, so this, it's going to be, the slope is negative 5,000 over 1, yep, times x, and there's a y-intercept of 5,000, yep. And so here you get negative 5,000 x plus 5,000. And so the height of the rectangle, or the area of the rectangle is going to be negative 5,000 x plus 5,000. That's the height of the rectangle times the width of x. So you get negative 5,000 x squared plus 5,000 x. And the triangle area is, so what's the height of this? So let me write this out. So the height of this rectangle is negative 5,000 x squared plus 5,000 x. The height of the triangle is 5,000 minus this, which just gives you 5,000 x. And so the triangle area is 5,000x times x divided by 2. And so you get 2,500 x squared. And now you can treat those. So now when you go to your cut, this is valid for all x's from 0 to 1. You can just treat it as two separate forces. The triangular distributed load of 2,500 x squared and the rectangular distributed load of negative 5,000 x squared plus 5,000 x. And then the internal loads. And the moment arm for this one is x over 3. The moment arm for this one is x over 2. So this is how I do it. There are a couple other ways to do the geometry, but I think the way to kind of store it in your brain is just the way I think about it. Break it up into a triangle and a rectangle, and then just go through all that geometry once you get there, you know. Like, don't try to remember it as formulas or anything. Just think of it as breaking it up into two separate forces and calculating those two separate forces that way. So then you go to Newton's second law. I'm not going to do it. Rotational Newton's second law. We can do it next time if you have any questions about it. But yeah, there is a way to do that one from the right, and it would be much easier to do it from the right. So to do it from the right, you would go. So first you'd calculate those external loads. Whatever this is and whatever this is. Yep. And you also have to do your internal loads using that other sign convention. I mean, the other half of the sign convention. So T like that, V up, and M like that. And yeah, you'll get the same answers that way. One of the practice problems, though, has a triangular distributed load like that and one like that, and then you're stuck, you know. So there are problems where you have to use this triangular method anyways. So I'd say just always go from the left. I think the more often you just do something the same way every time, the less likely you are to make dumb mistakes as it becomes sort of a habit. Any other questions? Okay, that's it.